Heat from the sun. So before we start talking about where the heat comes from, we got to talk about the life cycle of a star. Now, generally speaking, for a life cycle of a star starts out with just gas and dust that are just kind of floating out in space and kind of near each other. So their mutual gravity starts pulling them in and creating a nebula. Now, as they continue to move inward, they start to actually rotate around a center of mass of the entire nebula, and then it starts to get a formation, some sort of structure to it that's called a protostar. But it's not really a star at this point. It's just beginning to get into a star. And then the next part is when you actually get nuclear fusion. So when the protostar actually condenses down far enough and the heat increases due to that gravitational pull inward, the core of that protostar starts to get really, really hot. And this heat actually comes from the fact that you have a lot of gravitational potential energy when all these objects, this gas and dust that's really far from each other, and when they start moving closer toward each other, they increase their kinetic energy. And if you remember talking about heat, the amount of heat it comes from the amount of kinetic energy that an object has that in its vibration. So these particles come in and they start colliding with each other and hitting each other, and that goes into the vibrations, which creates the heat in the particles. And when it gets really, really hot and these particles actually get really, really close to each other, then they can actually start to basically coalesce. They start to combine with each other. And in that combination, when they combine, they release heat in the process, and that is where we get the nuclear fusion. And mostly it's hydrogen and helium that's combining in the nucleus of a star in order to give it that nuclear fusion. So now that it's officially a star, the fusion of the hydrogen and helium, this occurs for billions of years. And basically, when it's a star, it's referred to as a main sequence star, because there are a lot of different ways a star can come about. But this is basically the main process of what a regular star looks like. And then eventually that fusion slows down, and when that fusion slows down, the star expands and gets bigger and bigger. Now at this point, basically there are two possibilities. For a low mass star, kind of like our sun, it'll actually expand into a red giant. And the red giant, when it runs out of fuel, basically the outer parts of that star will get pushed off, and the elements that are in there, they'll basically shine because of the white dwarf that's in the center. So the center will actually become a white dwarf. It'll condense down to about the size of the Earth, and then the outer parts of it will be all the other elements that are in the star, and they just kind of get pushed away, turn into what's called a planetary nebula. Now, for a bigger star can actually become a red supergiant. A red supergiant, and the only difference between a red giant and a red supergiant is how much mass it has. A red supergiant has a lot more mass than a red giant. But when a red supergiant runs out of fuel, it will rapidly collapse and then explodes. And basically what happens there is you got the outer parts of the star and then the inner core of the star. And when that fusion runs out, basically the pressure, the atomic pressure, the nuclear pressure that's being caused by that nuclear fusion stops, and all of a sudden gravity is now the only force acting on it and pulls it in, because stars basically throughout their life have two forces acting on it: the pressure from the nuclear process is pushing out and the gravity pulling in. So when that nuclear fusion stops, gravity takes over and pulls that core in. Well, in the process, while the core is getting pulled in, the outer parts of the star are actually kind of drifting behind, and they're starting to come inward, but not as fast as the core collapses. But in the core's collapse, what it does is it actually rebounds off of itself, because with that collapse comes an instant of high pressure, and that high pressure starts fusing things that didn't fuse before, and it pushes that core back out. And the core that's going back out now meets with the outer part of the star that's coming back in, and bam, they collide. And that's where you get your supernova. And then in that process of that collision, basically everything else on the periodic table comes out of this supernova. Anything above iron, because a star can can fuse everything up to iron, because in nuclear fusion, energy is released in every fusion up to iron, but past that it actually takes energy to start fusing. So the star itself won't fuse past iron until this supernova, where actually a ton of energy is released and will cause some of the in those collisions make more massive objects. Now from here, there's basically two possibilities after a supernova. It either becomes a neutron star, which is a very dense, very small object, but it sends out gamma rays and X-rays, or it can become a black hole. A black hole is so dense that not even light can escape from its gravitational pull. And the main difference between these two, between a neutron star and a black hole, has to do with how much mass it has. A neutron star is massive enough to supernova, but not as massive as a black hole, and a black hole is extremely massive to where it'll actually, the gravitational pull will essentially be the only force we know of that's acting on the object, because it overcomes all other forces. So generally the life cycle of a star, we just went through the words and the process, but now I want to show a diagram that shows that gravity pulls the gas and dust in, and the gas and dust starts to spin. Because the particles, as they're moving toward each other, aren't perfectly lined up, so they'll kind of whiz past each other, and then they'll come back around, and they'll make a circular path. And that's actually how our entire solar system gets its orbit, is because these particles that were originally spread out, as they come toward each other, they start to spin around each other, and the entire solar system does that as well. And then that progresses over to a protostar. Now again, a protostar is not exactly a star yet, but it does start to get some structure to it. But then nuclear fusion starts, and this gives us into our main sequence star, and this is where a star is born. And from here we got two possibilities. We either become a red giant or a red supergiant, depending on the mass of the object. For a red giant, that will become a planetary nebula along the outside and a white dwarf on the center. But a red supergiant will actually supernova, and then you get an explosion out of that, and then you get two possibilities from there. Again, you get a neutron star, which is not as massive as a black hole, but will be a very, very dense and very small star left over that's sending out X-rays and gamma rays. In a black hole, we don't really know what happens inside of a black hole. We have some theories, but since we can't get any light out of a black hole because gravity is so strong, then we don't really know. All we have is essentially is conjecture. So the main difference in frequencies that you see from the sun, and you can see these here. This is the visible spectrum at one point in time, and it doesn't look like it's too extreme or anything like that. Our sun looks pretty calm and tame until you look at something like the extreme ultraviolet or even the X-ray. Then you can see a lot more that's going on inside of our sun. The X-ray, you can see that it's the corona is pretty obvious around here, and that's the reason the corona is not really seen in the visible, is mainly because the corona is so hot that it actually emits radiation a little bit above the visible range, with the exception of during a solar eclipse, where you can actually the moon will actually block out the sun, and you can see the corona around it. All right, so how does the heat get from the sun to the earth? Now that we know the structure of the sun, then basically we can start talking about how it gets. So we have in the core, we have nuclear fusion that releases heat, and by conduction that heat is transferring out of the core. The next zone is actually referred to as the radiative zone, and energy radiates out, which is aptly named. So the radiation is the transfer of energy through the radiative zone. And then the next zone, aptly named also, is the convection zone, and this is where hot material will rise up, and then it'll release its heat at the surface and then come back down to get more heat from the radiative zone. And then the last three layers, basically the layer right here, this is the photosphere. This is essentially where the light comes from the sun. And then the chromosphere is that layer that basically hydrogen is releasing some of that redness to it, as well as the mixing in with the light from the photosphere to give the sun its color. And then you have the chromosphere on the outside, and that basically is all where heat transfers from the sun to the earth through the process of radiation. So the entire process is, first you got fusion and conduction in the core, and then in the radiative zone you have radiation transferring, and then in the convection zone you have by convection heat is transferring up towards the surface, and at the surface you get radiation that comes out towards the earth.